our systems basically become distributed systems. And so usually your stock trading platforms, they are real time, they are event driven, and they are distributed systems. Okay, distributed systems basically increase a lot of stability, security, and availability. So any real-time event-driven system, if you want to enhance the availability, security, or stability of that system, you would want to convert that into a distributed system. Okay. So there are two types of distributed systems. There are client-server and there are peer-to-peer. Distributed systems basically means that you have a lot of replication. So if there was just one server doing a job, now you have like 5-6 servers, and they are communicating with each other to perform that job. And with the help of distributed systems, what happens is that you don't have a single point of failure. Now, since there are 3-4 other things that can do the servers that can do the same task, the same job, you don't have just a single point of failure. Think of it as hiring an employee. Like let's say you run a restaurant, you hire an employee, right, who's a chef. So if you had just one chef and if he doesn't come to work tomorrow, he falls ill, then that's a single point of failure. With distributed systems, you have higher availability. Your restaurant will be available because every day some of the other chef will be there. So that will be basically an implementation of a distributed system. And there are two types, like I said, client server and peer-to-peer. And what are the characteristics of a distributed system? So distributed system has a lot of replication. We have talked about replication, that all nodes, there are multiple nodes, so they're all replicated. They can all perform the same task. So even if one node goes down, all the other can perform that same task. They have heterogeneity. So they can have, even though they're replicated, they can perform a little bit of different functions as well. Heterogeneity in terms of how much RAM or CPU or processing power they have. They can have that type of heterogeneity also. And they'll all be working concurrently. Distributed systems, because now the work is distributed across so many servers, you can have enhanced speed. You can distribute. So somebody was asking in the questions, how do you distribute according to geography? You can have geo distribution systems, and you'll get more scalability. So what are the challenges? Now there are multiple challenges with distributed systems, right? So since there are so many nodes now, there are more opportunities for failures because more nodes can fail. Synchronization becomes a challenge because all of those nodes, because they're replicated, they all do the same thing. They now have to sync between each other. And scalability becomes a problem because you can't just scale it easily. It is highly scalable, but scaling is not that simple, straightforward. You have to think a lot before scaling a distributed system. And architectural complexity. So distributed systems is not something that anybody can come and handle. It has a lot of architectural complexity and a lot of experience to be working with distributed systems. Okay, there is this entire topic called deadlocks. I am not touching upon this right now. This is for your reference only. Like I said, you have the link to the board. Don't get confused. Some things are for your reference. And somebody had asked me in the chat about distributed tracing. So distributed systems need distributed tracing because obviously you have multiple nodes across the system. You want to be able to trace your errors in an easy way. So regular logging won't work. You need distributed tracing. Okay. So let's look at some diagrams to understand distributed computing. So you have your web application. Let's say it's built on Ruby on Rails, and you have 3 databases. All of them are doing the same thing. So that's distributed because now you have 3 databases instead of just having one database. Okay, so that's distributed. So the same query. Let's say you inserted a user here, but you can select the user for database 3. That's a distributed system because even though you inserted the data in database 1, they are all in sync, and you can get that query back from database 3. All right. This is what distributed systems look like. You have multiple servers and multiple databases, but they are all replicated. So as you can see, 4 databases, they're all replicated, and 2 servers per database, they're all replicated. They're completely homogeneous and they're replicated. Okay, this is a distributed system. So it doesn't matter if you make a request to this pair of servers or you make a request to this pair of servers, you will be able to you'll be able to get the right information back. Okay, that's the beauty of distributed systems. Right. Then what's the difference between centralized and distributed? So centralized, having just one database and having so many different servers accessing that database. Okay, or having just one server and so many front-end servers accessing that one back-end servers. Can be any example. But with distributed, you have multiple databases or multiple servers, and all are replicated, all can perform the same task. So even if one node goes down, you have other nodes to handle it for you. That's distributed. Okay, so multiple front ends, that same data is replicated across multiple servers. That's showing. Let's look at how a technology called Cassandra. So Cassandra is a database. It follows distributed computing to come up with the node. Okay. So I've written here Cassandra uses consistent hashing. This is how hashing takes place. These are all Cassandra nodes. There is only one node called the coordinator, and the coordinator node is the one responsible for talking to the server, and all the other nodes are talking to the coordinator node. Okay. And all of these nodes are replicated. So the Cassandra coordinator node decides which node the data will go into. So it will give it a hash key and it will send the data. The data that gets stored into Cassandra looks like this: key and value pairs. So key and value pairs, the coordinator creates a hash, stores it to the right node, and the coordinator node remembers which database has that information. So it's able to then aggregate that information back and send to the server. Okay. Cassandra follows eventual consistency. So that's weak consistency. You can read about weak and strong consistency and eventual consistency also. Then I've given an example of Medium.com. So Medium.com does something called as MapReduce. With distributed systems, the data that you store, you use MapReduce, and I've explained here how MapReduce works. Okay, so you use a lot of shuffle, sorting, and partitioning. And then now there are, with distributed systems, there are new type of architectures being followed. One is Lambda, one is Delta, one is Kappa. Okay, Lambda, Delta, and Kappa. These are architectures with distributed systems. And I have mentioned them here, and I've said that these are for your reference only. So completely optional. If you want to get deeper into distributed systems, not for everybody, right? So people with more than 7-8 years of experience, you can learn more about these architectures. Or if you want and attend any of my other advanced sessions, you'll be able to understand these deeper. But again, this is for reference only for this option, completely optional. And then a lot of people then wonder that we'll have an event-driven architecture, and then we'll have messaging queues and messaging streaming, message streams, and all of those. But what if they end up becoming the central source for failure? Okay, that's where you have distributed messaging. Distributed messaging basically has multiple nodes for messaging also, and there's multiple replication. So you have producers, you have multiple consumers, but for the messaging platform itself, there are multiple nodes. So even if one goes down, all the others are there. And I've shown you how P2P works. So this is client server. This is P2P, where in your torrent you have seeders and you have leechers, right? You can some of the people are saying that you can download files from me, and some people are saying that I want to download the files. And from multiple people, I can download multiple bits of the file, and then I can get the entire file, like Silicon Valley or Rick and Morty. This is how P2P systems work. So distributed systems are of two types. You've seen here, they are either P2P or they are client server, right? So mostly P2P systems is something that we won't be using. We'll be mostly using client server architecture. That's what we'll be using for distributed systems. And that's what the entire presentation is all about. And so you guys can come to slide number 8 now. Come to slide number 8. Let's look at slide number 8. Come to where it's written 8 on the presentation. All of you have the link to the board. Come to 8. Let's go one by one. So we have A, B, C, D, E, F, G, H, I, J, K. These 10 points we have. Let's cover those 10 points now together. Okay. So we talked about real-time systems. We talked about event-driven systems, right? Because real-time systems have to be event-driven systems. I hope that much is clear to you guys. And we're talking about distributed systems because for higher amount of security, higher amount of stability, higher amount of availability, we want to have multiple replicated nodes so that even if one goes down, others can continue serving us. That's what is the distributed system. Now, having considered that our system design, we are doing system design for a stock market trading platform. Having considered that, we want to now, we want to start looking at the different aspects. So the first aspect is logging. Now, logging is not very straightforward in a distributed system. You have ideally something called as a multi-stage logging. So here I've given you some cloud architecture diagrams of how multi-stage logging can work. So these are your services. You can have serverless functions. You can have normal microservices. You'll use CloudTrail to put all your logs in a bucket. And you can have CloudWatch to set off any alarms, or you can search for your logs. And here are the users. Users basically get alerts or they get search results from the CloudWatch service. Okay. And multi-stage logging can also look like this. So you have your microservices, your content delivery, your data store, your auditing, right? At each stage, you're having logging. So at each stage, you're having config logs. Everybody's writing to the config logs. Logs are getting stored in S3, and the logs can also be sent to SNS. You give notifications to the DevOps managers that, hey, this system is down or this microservice is down. So this is how multi-stage logging takes place, right? So I hope we are very, very clear that our stock market platform is a real-time system. It is an event-driven system. Event-driven because basically it has to respond to events. It's very reactive. We have to go for event-driven because making requests to every single microservice. So we'll have multiple microservices making requests to each other. Will slow us down. We'll have a lot of latency introduced into the system. That's why we want to have completely event-driven system. And we want it to be distributed because even if one particular node goes down, all the others still remain on the, are able to serve us. And this is why we are learning what is multi-stage logging, because for distributed systems, we don't have regular logging. We have to have multi-stage logging. Then we have, since we have so many microservices, we want to now start storing the data. The data storage also is not very straightforward. It's going to be distributed data storage and backups. So we'll use something called as Cassandra and Cassandra Medusa to start taking cluster-wise backups. So there are not just multiple nodes, there are multiple clusters with multiple nodes. And you're able to, even if one complete cluster goes down, so that's a very high level of failure. Even if a complete cluster of nodes goes down, you have another cluster completely replicated, which has a lot of nodes, and you can always bring back the system on. Okay, so all of this information is stored here. So where will we store? What will we store here? We'll be storing mostly our database backups. So whenever you have a system, you want to take backups of your data always, and the backups of your database you don't want to store in a place where it can fail very easily. So this is where we use distributed systems. We use Cassandra Medusa because it's highly distributed, and you're sure that if you're storing the backup of your database in some place, that place cannot go down, right? It has to be extremely highly fault tolerant. That's what you get with Cassandra Medusa. Okay. Now, in this 8th section, what we're talking about are domain-specific items. Domain-specific items mean that they happen only to this domain. By domain, when you hear about domain or domain-specific or domain under design, what you're talking about is that there are different types of domain. There's health tech, there is social media, there is fintech, there is streaming platforms, and this domain is a stock trading platform. That's the domain. Now, for this domain, there are some things that are specific to this domain. And when you walk into an interview, let's say you're going to interview at Netflix, for example. So at a company like Netflix, they would expect you to know more about OTTs and video streaming platforms. They expect you to know more about those. So that's domain specificity. If you go to an interview at a health tech startup, they would want you to know about healthcare and how health tech startups and how health tech infrastructure works. Similarly, for social media, for stock market, you would want to know about some domain specific things. So what are those domain specific things? Those are basically time series databases. Okay. So time series databases are very specific to stock market information because with time series, the way you store information is like, at this time, the price of the stock was, let's say, $20. After 3 seconds, it was $19. After 3 seconds, it was $18, like that. So you want to maintain a series of time. This is what time series databases do. Now these are very specific to this domain. Then you have analytics engine. Like I said, the reason you would choose one platform over the other for stock trading would be because of the analytics it will show you, the data it will show you, the charts and all that. So for analytics engines, you would want to use the best technology out there. So you could be using Druid, which is for aggregation and storing of data. You will use Apache Spark for streaming that information. You will use Apache Superset, for making sense of the data for showing you the analytics. That's what your analytics engine looks like. Okay. So right now, what we're doing is we are looking at domain-specific items for this stock trading domain, and we're going into detail on every single aspect. Okay. Now you have graph databases. So all the information, like let's say this person bought this stock and this person has bought all of these different stocks, and these stocks are similar to these stocks. So all of that kind of information are stored in graph databases. This makes it very easy for the stock trading platforms to recommend what should be the next stock, or could be other stocks that this person should buy, or which are right for him. So that recommendation information comes from graph databases usually. And then you have your ETLs, which is extract, transform. So I told you what is transformation. Transformation is like, let's say you'll get information in different formats. It could be XML format, HTML format, could be CSV format. But let's say you want it in a particular format, you want it in JSON because you want to show that information to the front end. So you use technologies that are called as ETLs, extract, transform, and load technologies. They extract the information from the database or from a data stream. They transform it and they load it back to the stream or the database. Right? So their main job is basically transformation. Extract and loading they have to do because obviously that's how they get the data and send it back. But transformation is the main thing, right? So ETLs are extract, transform, and load technologies. This is what they do. That's all their job is. They're also highly distributed many times, right? So we've talked about time series databases, talked about analytics engine, talked about ETLs and graph databases. Now I want to talk about C, which is distributed tracing. So this is what distributed tracing looks like. Right? So you have, let's say you have a shopping service, payment service, inventory service. All of these are creating their own logs, and you store them in a big hash map kind of a table where you're storing, what was the log created by which microservice. That's all that distributed tracing is all about. Basically, having the logs of all the distributed services. Then this is what your logging technologies can look like. You can have logs coming in from your load balancer, your Nginx, from your server, Apache, from your technologies like Golang. I've just shown that at every stage, at every level, you can be collecting logs. They can go into your log stash, they can get ingested into your Elasticsearch database. And Kibana, using Kibana, you can search and aggregate and show nice charts. ELK-Stack. So I just shown an ELK-Stack example, but I personally use a lot of Prometheus, and for backend and for frontend, I use Sentry. A lot of people use ELK-Stack, so I've shown ELK-Stack. ELK-Stack, sorry. All right. And then your domain specificity, domain specific, where for your stock market trading platforms, you use a lot of serverless functions. Serverless functions is something that not many people talk about because it's considered to be very, very new, even though they were launched in like 2014. But they're still not very widely used. But the companies that use them, they know they can vouch for them. They're very, very critical to their infrastructure and to their system. Serverless functions are very important in the new age, but not many companies use it. Not many people know about how they work. But I'll just try to tell you about how they work quickly. So serverless functions basically in huge complex architectures, which are event-driven, right? Specifically event-driven. These serverless functions like Lambda or Azure functions or Google Cloud functions, they do a lot of heavy lifting. So a lot of repetitive tasks, right? A lot of, I've written here, on-demand repetitive tasks. They're a perfect fit for those kind of tasks. They're highly efficient, easy to deploy, flexible, and cheap. They're very cheap because you pay as you go. So I'll write it here, pay as you go. You pay just based on your usage. Okay. So basically, the architecture that we're going for is a hybrid architecture. It has microservices also, and it has function as a service, which is fast. So two types, Lambda and Step. These are both types of serverless functions. And let me show you. So when you start out, you usually have a monolithic application. Then you convert into microservices. So why do you want to go from monolith to microservice? The reason is that I told you in the beginning itself of this session that you want to be able to have different considerations like AP or CP or CA. You want to have different type of priorities for every single microservice. So you can do that with the help of by converting a monolith to microservice, right? And also that is just one of the reasons. There are hundreds of reasons why you want to convert from monolith to microservice. So one of the reasons could be like, let's say it becomes very difficult for you to manage so much business logic in just one place. That's why you don't want to have monolith. Or you have a big team and you want to assign every single microservice to each team member. That's where you can have microservice. So microservice basically makes it very easy for you to manage the entire infra. And now function and service or function-driven architecture basically makes it even more easier, even more simple to manage that architecture. Because now instead of managing a complete microservice, you're just managing one function. That's it, just managing a function. So managing a Lambda function, you just have hundreds of Lambda functions there. And this is how usually the evolution takes place. But right now, what I'm showing you in the example is a mixture, is a hybrid. So we are using microservices, but many microservices are also going to be calling Lambda functions. We are using a hybrid of microservices and FAS architecture. So just examples of serverless functions. You have Lambda, Azure functions, Google Cloud functions, you have IBM Cloud functions, you have OpenFaaS, which is a very nice technology. I use OpenFaaS quite a lot. It's free, it's open source, you can deploy it, you can use it, it's brilliant. And now there are also serverless databases. So there's DynamoDB was always there. Now you have Aurora, you have MongoDB Atlas, Google Cloud Data Store, FaunaDB. FaunaDB is pretty nice. You can try and using it. It's pretty nice. So you have serverless databases as well now. Okay. These are serverless functions. These do quite a lot of heavy lifting in distributed and event-driven architectures. Because most of these serverless functions, right, they get triggered off from an event usually. So they do a lot of heavy lifting. They get triggered off from an event of heavy lifting, and then they perform the task. Don't put a lot of pressure on our existing microservices. So then I've shown you what real-time recommendation looks like. So real-time recommendation, you have Spark offline computing, you have Spark collaborative computing. Why do we have real-time recommendation? Because at real time, we want to be able to tell the user that, hey, this is the right stock for you. And this is based on a lot of information. It's based on what kind of stocks he's purchased in the past, what's happening with the stocks right now, price is going up and down. It's based on predicting the price information, what's going to be the price information later on. It's going to be dependent on the current socio-economic conditions and the industry news. So a lot of factors go into understanding which stocks that users should be buying. And that's how real-time recommendation of stocks takes place. I've also explained about machine learning engines, so how they work. Basically, you define the problem statement, you gather data about it, pre-process the data, analyze, prepare, evaluate models, tune models, and you publish those ML engines. Why do we need ML engines? You need these to be able to run your algorithmic trading platforms. So along with your main stock market platform that's running, you also have algorithmic trading going on. Like you have bots. You have put some users put rules, like they say that, okay, if this stock goes above $10, sell it for me. I don't want to be involved in actually going and manually selling it, right? So that's what your machine learning engines get trained for doing all of those algorithmic trading and doing recommendations, those kind of things. Okay. So we have reached point 8 now. Let me quickly take a look at what's happening in the chat. Okay, let me take a couple of questions quickly. Okay, so Krishna is saying notify other services versus inform external service. What's the difference? So Krishna, when we notify other services, we are notifying our internal services. Like let's say an email service needs to send an email out based on every single purchase of stock that this person is doing. That's notifying internal services. Whereas external services are, let's say, some other system that's waiting for some information from our system, some external company who wants to integrate with us. They're waiting for some information from our system, right? So that's basically informing external service. So Money has said, how does the front end get update every 1 microsecond? So Money, you can update the front end with the help of WebSockets. So front end and back end can be connected not using APIs, but using WebSockets, and then they'll be able to update in microseconds. So Virat is saying, how do we decide how many microservices we should have? So Virat, you try and divide your main monolith business logic into as many parts as possible. And that's when you start getting your microservices. So when you design the user flow, right, that's when you start understanding that for every user flow, you might want to have a microservice. You start with big macroservices where one microservice will have like multiple microservices, and then you start dividing that into small microservices. And you go to the point of you just have just functions running, and you have complete separation of functions. So it's an ongoing process. You keep dividing it, and you think that okay, this is separate from this complete module. Okay, so Sachin is saying typically these real-time updates are via WebSockets or webhooks. So Sachin, these many real-time updates are using WebSockets. Webhooks is when you want to notify, let's say, some other systems, you want to tell them that this has happened. So that webhooks are a little slower because webhooks means that you have sent the event there to the external system, but the external system, how does it react to the entire flow? They might be calling an API, or they might be calling, or depends if they are event-driven or not. So that's why WebSockets and webhooks are slightly different. Okay. And can't see any more relevant questions. Okay, so Dipanshu is saying, so it means Cassandra can have data loss in case of any node failure. No, Dipanshu. Cassandra, like I showed you, is having multiple clusters and multiple nodes. So even if one node goes down, multiple nodes are there. But even if one whole cluster goes down, multiple clusters are there to handle the failure. So Poonam is saying when to choose Mongo over Cassandra. So Poonam depends on which. So the reason we're going for microservices, again, one more reason is that we can have different databases, different types of databases for different types of microservices. So we can use Mongo in places where we just want to store a data dump, and Cassandra where the information needs to be very highly available, and it just can't be just can't get deleted. So I'll give you an example. Let's say you store your users' information or your stocks information in MongoDB, okay, and you're storing it there. But all the backup that you take of this information, because all the information that you have right now in the system, you want to have a backup of it. The backup database should always be Cassandra because that's highly available. It's expensive to run, so that's why you don't want to have all your systems running Cassandra. You just want to have MongoDB. You work off MongoDB in your stock market information service, and the database backup is where you're storing that in Cassandra. Okay. All right. So I think. So Hari is saying where to prepare for an in-depth system design. So Hari, this is what we're doing, preparing you for an in-depth system design. I didn't get the question. So Shivam is saying how estimation calculations are derived. So Shivam, they're called as estimations. You have to estimate or guess. Let's guesstimate also. So you guess that this is the kind of traffic you're expecting. But one good practice to follow is that whenever you're estimating these numbers and calculations, you always check with your interviewer that if these, the numbers that you're estimating for, are they fair or not? In the sense, you'd want to ask them, is 10 million a good number for the scale? So they'd say, okay, it's good, so you proceed. Otherwise, you don't want to proceed, or you want to change that number. Okay. Okay, which tech stacks are preferred used in? So Hari is saying which tech stacks are preferred and used in making a trading platform. So Hari, that's again an architecture decision, but as you can see here and there, I'm sharing information about tech stack. Like I'm talking about Cassandra, I'm talking about Neo4j Graph database, I'm talking about Elk stack. So I'm basically in systems, in places, I'm telling you which tech stack is preferred. Okay. All right. Let me check out the chats. Okay, so Rama Rao has mentioned the books recommended for system design. Perfect, Rama Rao. These are really great books. Especially the second book is really important. So in the chat, guys, if you can see the second book, Design Data Intensive Application, that's a very, very important book. Okay. So Bibha Bindu has said why Cassandra is highly available. So Bibha Bindu, I just explained to you Cassandra is highly available because it's highly distributed, right? That's the whole diagram I'm showing you. That's why. Gaurav Kabra is saying, how did you personally learn this? What are the resources? So Gaurav, I've been doing this for quite some time. You can read Medium blog articles, all these books that Rama Rao has mentioned. So you'll be able to learn all these things. Okay, so Ankit, nice question. Ankit is saying that initially that API data and all sources pass through ETL process and then shown. Okay, so Ankit is saying that we are using things like ETLs, we're using things like batch processing and API calling. How can all this be under 200 milliseconds? So Ankit, that's a good question. The answer to that is all of your things don't have to happen in real time. So when you take backups of your data, that's not happening in real time. That can be really slow. When you have, let's say, when you're saving data to an auditing service or to an archive service and auditing is happening, that doesn't have to happen in real time. It will be very slow. Okay, only two things have to happen in real time. One is buying and selling. The other is ticker price information. Only two things will happen in real time. Everything else you can, make it really slow. This is why we are following microservice architecture, because we know that two of our services are very critical. We want to prioritize high amount of consistency and availability there. Everything else can be slightly slower. We can have induced latency, not a problem. Everything. Okay, so I hope that makes sense. So Naren Kumar is saying everything is not crystal clear. So Naren, can you let me know what's not crystal clear? I can help you understand that. So Siddhesh is saying, does OpenFast relate to Docker? Yes, Siddhesh, OpenFast does relate to Docker. All right. Okay. All right. So let's learn for about 15 more minutes, and then we'll do a quick feedback check. But let me also launch a quiz so that I know that you guys are learning. Okay, so there's a quiz going on right now. Please answer this. So some people are saying the answer is A. The question itself says what are the three categories of real-time systems, guys? And the first A has only two options. So now let me run a quick quiz, one more. So Samrat is saying, let's check the main design now. Okay, Samrat, we'll start with the main design for 2 minutes time. Is that okay? 5 minutes time. But just one more question I want to ask you guys before we start. Okay, perfect. Many people have answered the right answer. So Raghav is saying one more question. You guys want one more quiz question, or should I continue with the teaching? Okay, so maybe we're saying yes, one more question. Okay, so one more question coming up. Okay, so guys, today's session is going quite good, as in it's very heavy. I'm sure you guys understand because this is a difficult topic. This is a difficult topic. It's a complicated topic, and like I said, it's one of the most advanced problems that you guys will be asked in a system design round. Okay, but it's very impressive that you guys have learned so much. Like I asked you 6 questions already, or like more than 90% of the people have answered all questions correctly, and Mohammed Farhan is winning. So I've asked you 7 questions, and 90% of the people have answered 7 questions correctly. So that's brilliant. I mean, even though this session is very heavy, right? A lot of right, the session is very heavy, but still you're able to understand so many things and able to answer the questions correctly. That's brilliant. You guys are really, really smart, actually. So now this question is slightly difficult.
Distributed.
Again, many people are answering the right question again, right answer. That's brilliant. Awesome. So what we'll do now is, even though I have a couple more questions, we can look at them later on. But what we'll do now is, what we'll focus on now is, we'll quickly go through. We'll start with going through the final system design, and then in between I'll keep jumping up to all the parts that are left. Now, guys, this session is supposed to go on for even more than 3 hours, but I know it's late at night. All of us are tired, so I won't do that. I won't go above, after, like, we'll just do 15, 20 more minutes and we'll stop the session. We won't go more than that. But there is so much more detail that I have for you. I just want you to know that, I came prepared for you guys, so that I didn't want to waste your time. So I came prepared with a lot of content. And we'll start, because a lot of people are saying to start with the final system design. We'll do that. We'll keep going through that. And quickly I'll touch upon all the other topics. Even though we could have spent like half an hour more on every single of these slides, I won't do that because you have the access to the board and I don't want the board to die. Okay. All right. Okay. So I think all of you guys have access to the board. All right. So let's go into the final system design, and slowly we'll keep jumping back into one of those sessions. And Shreya, in about 10 minutes time, we'll take a feedback. Is that okay, Shreya?
Yes, sir.
Okay. So guys, we'll be, yes, Raghavendra, thank you. I have taken excellent pains for creating this visual explanation for you guys. And we'll be taking the feedback from you guys in about 10 minutes time, guys, feedback. And that will be basically, you will be rating me how I've been as an instructor to you in this session. So I'm expecting good ratings from you at that time. But till then, let's continue for the next 10 minutes at least. And then after that also we'll continue if people want to stay around. All right, so this is our final system design, which is slide 22. It's slightly difficult, but I'll explain to you step by step, so you won't get confused. All of you have access to the file, so zoom in here on the last slide. Zoom in, everybody here. Now what I've shown you here are these corporate guys who want to do a lot of stock trading, like they're all Wall Street guys. And that's why I've used this particular image. Okay, and we have our servers running in edge locations. This is called as a CDN. We have not talked about CDN yet. CDNs are content delivery networks. If a person is in the US, if a person is in India, if a person is in Africa, we don't want the India guy to be calling the Africa server. We don't want the Africa guy calling the US server. We want to have edge locations. Ideally in their city. We want ideally the edge location to be in their city. So like, let's say if this guy is in Kenya, Kenya is a country, right? So let's say if he's in some city like Accra in Ghana, he's in the city. So or Cape Town in South Africa. So we want that city to have edge location of the content. Usually it's static content like logos, images, thumbnails, profile pictures, even some chart information that you want to show as static information, some GIFs. All of that information is static information you want to store in CDNs, right? And then now there are some ways you can store even dynamic information, which doesn't change very often in CDNs. I'm not talking about that because that can get slightly more complicated. Just talking about static information. Then I've shown here your front-end server. This thing here is your front-end server. I've written it here. This is the front-end server. So front-end server will have multiple servers. This is your complete front-end server farm. You can call it a server farm, which will have multiple front-end servers. Okay, they will also have replications. They'll have multiple servers. What I've also said is that this is a micro front-end. Micro front-end basically means that a micro front-end framework, just like you have microservices in backend, you have micro front-end frameworks in front-end, wherein you can use Vue.js, you can use React.js, you can use Angular.js, all three together in one single front-end file one single front end file that you create. UI, you can be using all three different technologies. So that's the beauty that you get with microfront. Okay, so till here everybody is clear. We're different people from different cities are interacting with our platform. They're being served data from CDNs. They have the front end servers. Obviously, if people are viewing, they're using the front end server. They're requesting from their browser to the front end server, and they're seeing the information. Now, the front end server stores a lot of image related information because every single stock that we have, those 10,000 stocks, they will have some metadata, they'll have some image information, okay, some logo information. So we'll store that in a bucket, S3 bucket. So Amazon provides S3 buckets. Buckets are basically media storage, very efficient for media storage, specifically designed for that. And then you have your read-through cache. In your read-through cache, you're storing your permissions, what all permissions that this user has access to. Okay. So let me show you how that works. So first, what happens is when your user he makes a request to the front-end server. Okay. The front-end server. Now, one confusion that you might get is like somebody had asked there that if we are using APIs, how can we have real-time flow, right? For real-time flow, only some of our things need to have real-time flow. I've explained to you that not our entire system doesn't have to have. Not every single microservice doesn't have to be real-time. Only two things will work in real time, which is buy and sell and showing ticker information. That's happening through socket. So front end, whatever you do do it through socket, and the socket is directly connected to the data stream here. Okay. So the front end is also connected via APIs to our entire backend. So the front end is connected with two ways with our backend. One is using socket for buy and sell information and for ticker information. And it's connected to our backend using APIs also. So obviously, when your front end works with your backend using APIs, that won't be real time. When it works using socket, that will be real time. So we have complete differentiation there. Now, your front end makes a request usually to an API gateway. Okay. So by mistake I've kept this arrow here. It should go here actually. Your front end makes a request to API gateway. And external APIs also make a request to an API gateway. So API gateway is like the guy who's guarding the door. API gateway is the only component or the single point of contact for your entire backend. Your front end cannot directly talk to your backend. Your API gateway is the person in between. Why? You'll ask me why is API gateway in between? API gateways in between because API gateways has many logic, many layers of logic and algorithms to help you filter out the right valid requests. You don't want bots to be making requests. You don't want hackers to be making random wrong requests. You want to be able to filter out and validate those requests. That's why API gateway is there. That I don't want my entire backend system to get infected by something. So API gateway will be responsible for firewalling, for rate limiting, for validating requests, for checking the authenticity of the user, for white listing and blacklisting my IP addresses. All of that can be done by the API gateway. I hope that's clear, right? Then you have load balancers. So API gateway then forwards the request to a load balancer, and this gets forwarded to mesh. Mesh is also called as you guys may be knowing about service registries. Service registry is something that stores the information about every single microservice. Okay, and there could be multiple of these. So you don't need to have just one mesh or service registry. You can have multiple service registries. And what happens is it saves the IP addresses or the location of each microservice. Now, when you start out as a system, you have just 10, 15 microservices when you start out. But when you become bigger as a system, you realize that every single business logic needs to have its own microservice. So you end up with thousands of microservices like Netflix. Netflix now has thousands of microservices. They use chaos engineering to actually test all those microservices at one go, right? So when you have thousands of microservices, it's not possible for your front end or your API gateway to know which microservice exists on which IP address or which container and so on and so forth, right? So you need a specialized technology called service registry, which will be able to have the location of every single microservice and able to track it basically. So your front end makes a request. Your front end, which is using micro front end technology, which is using Vue, React, and Angular at the same time, it makes a request to your API gateway. API gateway makes a request to load balancer. Load balancer, then load balancer you already know now, right? It decides which of these is available, which of these has less traffic and more bandwidth. It then filters the request to those guys, to that particular service registry. So load balancer gives that request to the service registry, and that from the service registry, the request goes to the particular microservice. So in my case, when I'm starting out from my front end, the first request will go to obviously the authentication microservice. Authentication because obviously I want to log in the user, right? I want to log the user in. So every single microservice, this dotted line that you see here is like a zoom in. I've zoomed into every single microservice and shown you what it looks like from the inside. So what does a particular microservice look like from the inside? It looks like this. It has 3 servers, 1 load balancer. This thing that I've shown you here, weighing machine, is like actually a load balancer. I've shown a nice icon here to make it more interesting. This is the cache. This is the cache. This is a database level cache because you don't want your backend to be making requests to the front end again and again. You want to cache some of that, and you don't want your service registry to actually make an entire request to the server. You can cache some of the information that is used very often at the cache level itself. Okay, why do we use so many caches? We use so many caches because we want to reduce the latency. Latency is basically how fast can you respond, how less is the distance between every single event happening. That's latency. So you want to have as less latency as possible. So you have so many caches because it reduces the time to actually query the servers, query the databases. I hope that's clear. Why do we have load balancer here also? So we don't only have load balancer here for service registries, but at every single microservice, we have a load balancer because every single microservice has 3 servers, and there's a load balancer to understand, which server is available or has less traffic, and it can basically send the traffic to that particular server. So I hope this is clear. Let's do a quick quiz. So Zealous Macwan is saying, is Mesh also microservice? No, Zealous. Mesh is not microservice. So Rohan is saying you scale up API gateways too. Yes, Rohan. So API gateways you can scale up. They're mostly managed services. Okay, so let me do a quick quiz just to see what's happening. Okay, so this is one more quiz. So Siddharth is saying, what is microservices to common man? So Siddharth, okay, so let's say you have a complete backend system. You have multiple, you have a front-end server and backend server very simply. And backend server has many different type of logics. Like it has, let's say, buying and selling and ticket information and invoicing information, emailing service. All of these are different functions that your system can do. You don't want to have it in just one place because that's very difficult to manage. Because every time you update anything, everything goes down together. You don't want one thing to affect other things. That's why you start dividing things into microservices, because you want to have separation of concern. Separation of concern is a very important topic in engineering. So I've seen one more interesting question here. Yes, console and Kong API or API gateways. Okay, so Saurabh Agarwal has said why 3 servers in each microservice. So Saurabh, at each microservice level, especially the ones that are very important like authentication, authorization, especially these ones, you want to have as many servers as possible, at least 3, because then you have some amount of replication. So if one server is down, you don't want the entire microservice to go down. So even in microservice level, you want to have multiple servers. So I hope you understand that. All right. So can you explain the last quiz question? The question is done, though it's gone. So what does the first cache server do? So first cache server is for, you don't even want the request to go to the server. You want to just, send it back from the cache. That's there. And then you have like, one at the database level as well. All right. So So Deepak is saying unable to view the board. Deepak, you already have the link to the board. I hope you have the link to the board. So view it. All right. So guys, I think the time has come for a quick feedback. Feedback is where you will have to give me rating on how the session was. If you give a 10 rating, then that basically means that you would be attending more sessions with me. If you give me a 9 rating, it basically means that you won't be attending session. We'll continue after this feedback. So there'll be a feedback poll right now, and if you give me a 10, then you will see me more often. If you give me a 9, then that basically means